expected range for that variable. I think that's good enough. Maybe we can now look at variable assignment. How do we later on in the program or in the code, the VHDL code, do you do variable assignment? Just like in programming, you declare your variables, and you may need to do the assignment later on in some other part of the code. So for programming, software programming, it's not really a big deal. If you declare integer sum up there, column, then somewhere in the code you'll just say sum equals maybe a plus b. There is no much difference. There is no much syntax difference between declaration and assignment. But in VHDL, there is some key differences on how you actually declare and also how you do the assignment. You give some values to that variable later on. And this is the difference comes with the operator that you use. So for example, in the signal assignment, you can see when we are doing the declaration, the initial value was given with this colon equals. But when we came to the assignment, we were using this operator, the less than equal to. So this is actually how you would assign values now to the signal later in the program. And because it is a signal, there is the aspect of time as well. So in the variable, which operator do we use? In this case, before we give the operator, we can make a note that in variable okay. Apologies for that. I lost the network. Yeah, so I was saying for the variable assignment, it takes effect immediately. That is as opposed to the signal object where the assignment it takes place after some given time. That time you can give it explicitly um, in the assignment, or it can be implicit such that it will be after some small time delta if you do not give that time there. But for variable assignment, it takes effect immediately. So that is one of the differences between variables and the signals. And the other one is the operator used for the assignment. So variables are assigned using this operator, colon, post, operator. So that's another difference with the signal data object. So for example, if we have declared some variable up there, so in this case maybe the sum. So we have already declared the sum up there. We may want to assign some value, and we'll do so as such. Yeah. So that's an example of a variable assignment. So the difference between the signal and the variables, one, we have seen that the variable assignment takes effect immediately. The signal assignment, it has a time property. Variable has no time property, it is instantaneous. Then the other one is the operator that we use for the assignment. For the signal, we use the less equals operator. For this, we use the colon equals operator. And I think that's good enough. For that, we can proceed to the third data object, which is not really different from what we have covered. And so the third one is constants. And I think this is self-explanatory. So this is it's an object which is initialized to a specific value. Upon completion, and of course, because it is a constant, it cannot be subsequently modified. So how do we declare a constant? So for constant declaration, just as the previous data objects, we start with the keyword for that particular object. So for the variable, it is variable. For the constant, as you can guess, it will be constant. That is the keyword. constant, and then you give a name, a user given name. So we have a constant name, user defined or user given, then the colon, then you give the type. Is it a bit? Is it a standard logic type? Is it an integer, and so forth? So we have the constant type. And then, being a constant, definitely there is some, the value of that constant. So you give it some value. Excuse me. Some initial value. I think that's we can finally look at the another data object. You can read more on this. We will not be getting into further details than this. Our final data object is a file in VHDL, and this is only used for simulation. As you can guess, this is a data object used to access files, on the platform that you are working on. So we can note that the file type is used to access files on disk, and is only used in simulation. So when you talk of simulation, that is in your test bench, code. Therefore, hence it cannot be synthesized. When you talk of synthesis, we mean implementation in hardware. So we cannot synthesize that particular one. But for simulation purposes, we can use it to, for testing our circuit using a test bench. So as far as the data objects are concerned, that is what I think are the key ones. The variables, the constants, the file, and also the signals that we looked at previously. So I would want us now to very briefly look at the data types. So we have the data objects and now the data types. So let's look at the VHDL data types. So as we have already seen up there, that for each of those data objects, they must be declared or assigned with a data type. So if it is a signal, a data object signal, then it also needs a signal type. If it's variable, we need the variable type. If it's a constant type. So we can note that in VHDL, every signal, a constant variable, etc. must be assigned or declared with a data type. The data type and can hold or return only a value of that type. So among the various data types within VHDL, we have a few categories of such data types, starting with what we refer to as the enumerated types, data types. So that's a blanket category that now has specific data types, for example, the bit, Boolean, character, etc. But as a group, they are referred to as enumerated data types. So what are enumerated types? And this is not just in HDL, but you will find this term in other programming languages as well. So an enumeration type this is a type with an ordered set of values. And this ordered set of values are called enumeration literals, What we mean by that is a type in which the exact values that particular type so as an example, we have the standard package, that is the IEEE standard package. We can note that remember when we introduced the code structure of VHDL, we started with the library part, and in that library part, we said there are three types of libraries. The library standard, which is inbuilt, and we said it contains definitions for standard data types, for example, Boolean, integer, bit, and so forth. We also have the library IEEE, which is not built in and must be added. Yeah, so that's what we are referring to as here. That library standard, the STD, It provides a variety of predefined it provides a variety of predefined enumeration types. For example, what are the enumeration types that we find in the package standard? We have, just to mention but a few, we have the bit, we have the boolean, we have the character, and others is just an example. So for this, we are saying that when we talk of enumeration, it is one in which the exact values that the type can take on are defined. So when it comes to the bit, it is defined as a type that can take. So let me just put it in a better form. So we have, when you talk of enumeration, we have a type, and then the values that it can actually take are also defined, so they are known. So we have the type, and we have the values that the type can take on. So when we talk of a type a bit, the values that it can take on are, anybody? Which values can data type bit take on? Anybody? Is that correct? So we have 0 and 1. Okay, thank you, Brian. Then the boolean, it can also take the values that a boolean can take, and this is true in other programming languages as well. Can either take a false or true. Of course, there are ways of representing that false and true, maybe 0 and 1. Then if we talk of a character, the values that a character can take are also defined, and those are any of the 256 ASCII characters. So that is one group of data types under the enumerated types. But those, what we are giving here, are the ones predefined in that particular library package. But you can also define your own enumerated types. So we can also have user defined enumerated types, and I think you must have encountered this in other programming languages. For example, in C, you can also define your own enumerated data type. So here we note that this is one in which the name of the type is specified by the user. And the user also gives the values that particular type can take on. So in addition, the user also gives all possible values that the type can take on or can assume. So the syntax for enumeration type definition. The syntax for that enumeration definition. So you start with the keyword type. Then you give it the user-defined name. So the type name, which is now user-defined. Then keyword is. So as we say, the VHDL is quite verbose. So kind of coding, kind of sentences. So the type name is. Now you give the values that that particular type can take on. So inside these brackets, you give the various literals or values that it can take on. So etc. So for example, let's say you're doing a circuit that has something to do with traffic lights control. So you may wish to define your own type, the enumerated type, and you call it traffic lights. And because they are specific states or specific colors that a traffic light would normally assume, you give those particular colors or states. So as an example, if you were to define your own kind of traffic light type, this would be the syntax. You can choose capital or small letters. So you are giving it a name, maybe traffic light is, and then what are the possible or what values should your new type take. In this case, you can choose whatever names you want to give your literals, but for to make your code clearer, maybe you can just give the actual colors. So you say there will be a yellow value, a green, there will be red, and so forth. So that is a user defined enumerated type. And now in your code, you can now actually use the traffic light as a data type, just the way you'd use a bit, a boolean, a character, and so forth. You can now use traffic light as another data type. But of course, now you know that data type can only have these values. Just like the betas, you can only have a 0 and a 1. The same thing with your traffic light, you can only have these values, yellow, green, red. So if you say traffic light equals blue, then that will be an error as far as the VHDL is concerned, because your traffic light is not defined to take in blue as a value or as a valid value. So anyway, I think that is enough for enumerated types. Remember, these are general categories of actual data types. The data types here are, as examples, the bit, boolean, character, amongst others within the standard package. And also we are saying you can define your own enumerated types. Another data type category, general category, is the range. So we have the range types, and as the name suggests, these are data types that actually have some, you can define some ranges. And I think we have already seen one of them when you are doing the variable assignment or the declaration. We used a data type and also some range. So this is one that can take on any value within a range. And examples here, some of the data types that can be regarded as range types. We have the integer, which we have already used somewhere up there. So, and very quickly, so we have the type, and we have the values. The values that the type can take on. So we have the integer. These can take on all numbers. Between from negative 2 to power 3 power, that's 2. You can counter check that to positive 2 to power, that's 2, because in VHDL the integer is that 2-bit. We also have the type real data type, and these are fractional numbers. You can take on values of fraction numbers between negative 1.7 exponential 38 positive 'This, so the real is also at that 2-bit floating point value. Yeah, I think these are not new things. So we are only categorizing them now under the range types, but you know what is an integer, you know what is a real number. Maybe the last thing we can mention under these range types is that the values of these types, that is for integer, that is for integer and real numbers. Are indicated by simply using the number without quotes. So for example, if you want to assign a number 33 a fractional number 3.14, you assign them as such without any quotes. I think that's good enough. Examples, we have already used an example in our previous, in the variable assignment. So for example, you can have an integer 1, 2, some value, maybe 100. You can also have another example. And the ones in blue, these are keywords in VHDL down to maybe to 0. So you kind of counting down, counting up. We also have up to and so forth. Then I think as far as the data types are concerned, we have others. Let me see which ones. So maybe I mentioned the vector types. We have the vector types. And the data types classified as vector types are the ones that consists of a linear array of scalar types. So for example, we have the data type bit vector, and this is defined in the standard package. So that's a data type, and this is a linear array. A bit vector is a linear array of type, the bit. We also have a string. We also have a string, and this is a linear array of type character. So for those who have been keen, you realize that these data types are not that different from what you'd find in software programming. You'll find similar concepts there. So they are not that different. But of course, because this is hardware programming, as you read further, you will start noticing a few differences here and there. So I think in the interest of time, we want to stop there. Maybe we can mention other types. We have physical types, and in VHDL, time is the primary supported physical type. We also have vector. I think that one I've talked about. We can talk of the array type. That's also another type in VHDL. I think we that is good enough to allow us to proceed to some examples. Some VHDL code examples. But what we have covered so far is, is just an overview of some of these things. The data objects, the the data types. There is much more that we are not able to touch on in the interest of time. So I hope we'll be able to read a little bit further on some of these things, especially the data types, the data objects. How do we declare? How do we initialize? We should also be able to read a little bit more on the design styles, the data flow design style, the structural design style, the behavioral design style. We mentioned them and we gave a few points on those, but they were not exhaustive. So you can also investigate them a little bit more. So we will take a short break, 5 minutes. When we come back, we can now do some circuit example. How do we come from a circuit to the actual HDL code, and we see how we can also simulate that if time allows. If not, we'll be able to do that tomorrow in our morning session. So let's meet at 3:15. It's 3:10 now, 5 minutes. We meet at 3:15. Okay, we can continue. So we have done quite some review on VHDL, the syntax, and now we want to at least have a feel of a VHDL code, from a circuit schematic. So this is the circuit that we'll be using for our example. Just a simple circuit for illustration purposes. And apologies for the background noise from the computer. So this circuit, the Boolean equation for this, and you can verify that later. Is given as such. So you want to implement this circuit in your, let's say for example, your an FPGA is your target. So you want to implement this circuit in your FPGA. So and you want to use a VHDL for that. So how do you proceed with this? So we recall our code structure, the VHDL code structure. We said it has how many parts? How many parts? Somebody? Yes? Anybody? VHDL code, the structure, how many parts?
5.
5. Which and which? Did we talk of 5? Somebody else? I don't think we mentioned. Yes, which and which? Mm-hmm. Yeah, okay. Yes, I think that is what we mentioned, and we can all agree on that. So just for purposes of the notes, to highlight that in our code to describe the circuit, we expect to have a library part. We also expect to have an entity declaration part. And finally, we expect to have the architecture, part. And it is within this architecture part that we actually now give the code for the circuit itself. And we said we can do that in three ways. Which ways are these? Which styles are these? The design styles? Somebody? Remember, for the entity, this is more or less a black box, but the real circuit is defined in the architecture part using any of the three styles. Which and which?
Data flow,
The data flow,
behavioral,
behavioral. Okay, thanks. And structural. And remember, for structural, once you do that subdivision, you can actually have each of those more components either in data flow or in behavioral design style. So our code structure will look as this, and I will be using okay, just a minute.
Just want maybe assist on that, because like some books people to
Sorry.
like if you look at some books,
Yes.
for some references it do give like 5 or more parts of the VHD code. Like maybe you want to bunch different entities together, so maybe you can have the configuration part and the package declaration. And maybe you have different entities you want to bind together, as well as you want to embed different entities together as well. So I don't know whether they're just exactly 3 parts of the HVDL code.
Okay. Yes. At the very basic, especially in most of the circuits that we'll deal with, these are the three major parts: the library, the entity, and the architecture. But as we said, for example, in the structural design style, you will have actually standalone VHDL codes, which now you will join together with from a top module or a top entity, and then you will join or instantiate the other entities, which we call the components. So in that case, it may look as if it has additional parts, but I think the bottom line is that even in those examples, well, I've not seen those examples, but I would assume that these are the main parts there: the library, the entity, and the architecture. But of course, if you found it in the reference books, if there is any part that is not here, maybe you can let us know. Is there any part that you have encountered that is is outside of this, the library entity and the architecture?
No, I've just given the additional one, but the major parts of this, the major parts are just the ones you did state. So maybe like that, yeah.
Okay, I think then that is okay. Of course, maybe people will define parts in a different way, but the major ones really are these. So let us do this example because of time. We'll do that on the notepad. Let me see. I don't know how we can. Somebody knows how we can. Okay. Yeah, I think we can zoom in. That's good enough. But we also need to have our circuit visible somewhere. I think yeah, that's good enough. So and so without wasting time, we said our library part, from our previous notes. I think it's here. We said it's a boilerplate code. This is what you will always find in most of your code. So we can as well just copy this and paste there. So library IEEE, use that particular package. That's it. So we'll start there. So we are starting with the library part. So as a comment, okay, I think, okay, we will have to save this as a VHDL code format, not a text file. So this is yes, we'll save this as the VHDL file. We can also have Verilog file if we are doing in Verilog, but in this case we want to use a VHDL so that it's able to highlight the keywords and so forth. So this on top of example 1, and in this case we are starting with the library part. Okay, so for the library, the keyword is the library, and you can see it's highlighted in blue because it is recognized as a keyword in VHDL. So library IEEE, also you can see it recognizes that, and the other one was use. We have to use the IEEE standard the library is the std logic. You only need to do this once, and more often than not, you just be copying that and pasting in your code. And we need to minimize this, but I hope it's still quite visible. That's okay. So as far as we are concerned, that's really it. So the other two libraries, the work and the standard library, are already implicit or already inbuilt in this because it is a VHDL code. Yeah, so we are done with the library part. So what is the next part? the next part, it's the entity part. So we have the entity, the entity declaration. And for this, we give the syntax of how we declare that. Maybe for purposes of that, we can just bring this up here so that what you see, whatever we are typing is not new. It's something that we have already mentioned. So you can see the syntax for the entity, and that's exactly what we will do. We only need to give a name to our circuit, and then the various ports that are available in our circuit, as a black box, and that's it. So that's exactly what we'll do here. We start with the keyword entity, already highlighted there. Then the circuit, name of our circuit or name of our entity. Maybe we can just call it example 1. I think that's good enough. So this is user given, and then is port. So we give the various ports within those brackets, and finally we'll end our entity. And which entity are we ending, or which circuit are we ending? It is the example 1. So this is the entity declaration kind of template. So in here we now put the various ports, inputs and outputs. And that's it. And for this case, our inputs are A, B, C, and D. We want to give them the type standard logic, because we said more often than not, your ports will be using the standard logic type, because it allows 9 values that that particular signal can take. If you were to use the bit type, then our inputs can only take values 0 and 1, which may not be the case when it comes to the actual hardware. So the standard logic is the default type that you would want to use in most of these cases. So our ports, sorry, I don't know. Our ports is we have A, we have B, we have C, we have D, and these are inputs. So the mode is in. You can see it's highlighting in blue because it's a keyword in VHDL, and of type standard logic. So yeah, that's it. Then for our output we have F, and this is of the mode out, and we still want to use the standard logic type, and that's it. Yeah, so whatever circuit you are given, however complex it is, your entity will simply be of this structure. Just make sure you have your inputs and outputs defined, and that's it. So the library part is complete, the entity declaration part is complete, and then finally we do the architecture. We do the architecture declaration. So in this case, now remember, we said in our architecture part, now this is where we have some choices that we can make. Yeah, we can do data flow, behavioral, structural. So let's say that we'll be using the data flow design style. That is what we'll be using. So how do we go about this? Of course, keyword architecture. There, we give it a name, user given name. So what we call it, let's just say maybe data flow architecture. This is user given, whatever you want to call it, and it is of which circuit? It is of our example one. I may have to, okay, maybe I can just expand this a bit. It is of example one is, we said, it's quite wordy, so kind of like Python. We'll begin, and at some point we will end that architecture. Which architecture will we end? It is the data flow architecture that we have there. And that's it. Yeah? So this is basically the structure of the structure of our architecture part. So keyword architecture, give it a name. It is of which entity. We have our entity there, example one, which we declared up here, and then begin. And so in here is where you will have your circuit definition, or circuit definition, which can be many ways: data flow, behavioral, structural, and so forth. So remember also, in the data flow architecture, we said we could use there were three things we could use. There was the Boolean equation. There was I think there was the selected signal assignment. Let's just confirm that. Whether we in the data flow, yes. So we could use Boolean equations. We could use conditional signal assignments, selected signal assignments. We didn't get into details on this. You can kindly review. But for us, for purposes of this example, we'll do the Boolean equation, and this is using simple signal assignments. So here we use a Boolean equation, and because our circuit, we already had a Boolean equation for this. So when we talk of the Boolean equation, we use signal assignment. We have just reviewed the data objects and the data types. For the data objects, we have reviewed the signals, variables, constants, and files. For the signals, we said, how do we do signal assignment? Which operator do we use for signal assignment? Because that is the operator we need to use here. Which operator is that for signal assignment? Those who have been following.
Less than or equal to.
Yes, thank you, Emmanuel. That's very correct. So for signal assignment, we use less than equals to as the operator. When it comes to the variable assignment, we use the colon equals. So we need to be very alert on that. So Boolean equation is already given here. So this is just what we now translate into VHDL format. So our output is F, and this is given by what? Now this is where you use the signal assignment operator, less than equals to. So we have the A and not B. we have A and not B. You can see it's highlighting the and, the not, because these are already defined in some implicit libraries within the PHDL framework. So A and not B, nor not C, not C. Oh, sorry, this C is in capital. Not C and not D. So surprisingly, we are done. We are done with our code. If we are using the Boolean equation for our design style, the data flow design style, then we are done, because this equation here is exactly what we have here. A and not B, nor not C, and not D, and that's it. So as far as our example is concerned, we are okay with that. We have finished library part, entity part, and the architecture part. But of course, this is, as you can see, this is not bad. Doesn't tell us anything. It at least it highlights some of these keywords, but it doesn't tell us anything else. Is our code correct? Is the syntax correct? How do we compile? How do we simulate this? So that is the next thing we'll need to do, and we will not be able to actually run through this simulation in this session. We'll do that tomorrow. But in preparation for that, I will highlight a few things that you can also do on your side to make sure that. I'm not sure why this is behaving as it is. It seems it's not zooming. No problem. Let me just. Okay. We continue. I don't know what has happened, because this view is not something I'm familiar with. You can see a lot of things yeah, this doesn't look okay. Anybody that can probably point out what I need to change with the view. Okay. Yeah, it's yeah, I think yeah. So we have our code, which is here, but we need a way of actually compiling, simulating, and all that. And in preparation for tomorrow's session, I would want you to also have the necessary tool or tools to enable that. So let me just see what you need to have. Then we can go through that. So this so VHDL code, C compilation and simulation. Now here I'll try to be very fast on this, and this information, of course, is out there. So from what I've interacted with, as I said, we have the main vendors, and here we talked of what do we call them, the Xilinx, and I said this was bought by AMD, or they merged. I don't know which way, or they, yeah, I think they were bought and now referred to as AMD Xilinx. So we have those devices, and as you can imagine, they have their own ecosystem. So here you'll find various software. I've used Vivado, so Vivado, and this will allow you to be able to write the code targeted for these Xilinx FPGA devices, and to simulate and to generate the final file that you actually load on their FPGA. So I've used the Vivado software, and what I know is this is heavy, quite heavy. I think, I don't know latest, but upwards of more than 20 gigabytes. So if you want, you can install that. I think they might be having some other variations of the same. If you don't want the full Vivado software, I think they have some web based or web pack variations which you can install if you so wish. But at least this is something I've used. It's really, if you really want to get, this is not just now about classwork, but Yeah, well, it uses Verilog in its name, but it also actually simulates for VHDL. So please do this by tomorrow. It shouldn't take more than 2 minutes to do that. And then when we meet tomorrow, we shall be able to proceed with the simulation. So tomorrow we'll do simulation. Remember, to simulate, you need another code known as the test bench. So what we did today was coming up with our circuit code or our entity code. But for us to simulate this code, we actually need to write another code known as the test bench code, which now we use to simulate this main our circuit code. So tomorrow we'll be covering that simulation and test benches, and this is on Icarus. And we'll also be able to do the same on Vivado, because as I said, I've used Vivado so that you can, for those who are not installed, you can see the differences between the two. Of course, Vivado is a full-blown software for FPGA development. So, and this will complete our sessions as far as FPGAs are concerned. So please make sure to have the Icarus Verilog ready, so that even as we do in class, you can also be taking the same steps on your machine and see whether we'll be arriving at the same results we'll be getting. And then just as a summary, we'll look at, or in conclusion, we'll look at Vivado, do an example there, the full development for an FPGA target. And I also have an FPGA board, but of course now you will not be able to see that, but at least you'll be sure you get access to the board. You can upload that code and it will run, or that hardware implementation will be done on the FPGA. So I think that's enough for today. Let's meet tomorrow, 8 to 10, to finish up and wind up on this FPGA and VHDL aspects. Yeah, I think that's it, unless there is a question, comment. Any question or comment? If there isn't, then let's meet tomorrow.